Nagel's.
Those two.
There should be a Nagel here.
Sorry, I should have
No,
said
no,
that.
no, don't worry.
Great.
Thank you. Okay. So you see the title there, and the first thing that might jump on you is, what is this lattice-enabled business? So I'm going to spend a graphic talking about terminology because it's one of the ongoing entertainments in this field. Of course, it started out as cold fusion. The low-energy nuclear reactions came in, and it has now, LENR has attained something of a name recognition, but low is a relative word. You know, low to Rob is near absolute zero. You know, in this field, it's room temperature. So I invented this lattice-enabled thing to keep the LENR, but to more accurately describe, get away from the low business. Lattice-assisted is also used. Chemical-assisted is a term liked by chemists. That's all right. Cold fusion nuclear reactions has been used, but not much. Then you have some regional favorites, as you see here, Russian and a couple Japanese names. The most recent being MDE, a new program in Japan between Kobe and Teknova. The Fleischmann-Pons effect is a rather good moniker for this because it is encompassing. It does give recognition. Now, recently, I've been touting this thing called SANER, for Safe Nuclear Energy Release. It has nothing to do with the relations between myself and the hot fusion community, to which I used to belong. Okay, but it's actually a serious suggestion. The field, of course, is part of this subject is part of the field of condensed matter nuclear science, and there's an international society in the UK. So the outline for the talk, 3 parts, one on the technical challenges, one on the other challenges, and at the end, I'll try and set this subject in the broader energy context for the United States. This is going to be a much more qualitative talk than some of the ones that preceded, but it will overlap some of the points made in the earlier talks. There was emphasis on the scientific method, and this is a very, very brief graphical rendition. You have ideas, we do things, do research, get results that are subject to criticism. Now, we're all critics. It doesn't matter whether we're wine critics or restaurant critics or physics critics or all. It's a normal part of human existence. And the definition of the critic there, reasoned judgment of something. You know, the emphasis on having in your head the material that's necessary or in front of you in order to apply reason to the problem at hand. That's absolutely fundamentally necessary and is too often not applied in this field. 2 kinds of criticism. The self-criticism is indicated by the little do loops at the top. Let's see, these, okay, and then the ordinary criticism that results. So I'm emphasizing this for the reason that there's a certain tension over criticism in this field. But as far as I'm concerned, since it's a scientific field and criticism is fundamental to science, that it's not only to be tolerated, but is fundamentally necessary. Now, there are 2 kinds of research. You can do things sort of offensively. You do it because you want to or because it may be useful, or you can respond to the criticism of others, okay? Now, the choice of terminology here has nothing to do with the fact I worked for the Navy for 4 years, nothing, okay? Now, I'll show you 3 kinds of defensive work that are in this area. Graphic each on errors in measuring input energies, which were talked about already, energy stored in lattice defects in the palladium, and then the small energy changes that may occur in many water molecules that are present in the electrochemical experiments. So first, talking about input energy measurements. The electrical errors in the electrical measurements get emphasized, but energy can come into these experiments by means other than electrical. Okay, so we'll take a look at that very briefly. Concerning the electrical, it's power times time for energy, and the power is the voltage times the current. And there is just simply no question that instrumentation is available to measure fast transients and the other effects that were talked about in more detail by Rob Duncan at the start of the session, and that there are no substantial errors in the measurement of the electrical energy input in the good experiments, okay? So that, which was emphasized by Garwin in the 60-minute show, is a red herring as far as many of us are concerned. Now, the second point about other energies, you have conductive, convective, and radiative means of energy transfer. Well, the cells are hotter than the surroundings, so you're not going to get uphill conduction. Okay, the conduction will be from the outside to the inside. And similarly, the radiative heat transfer, the net, will be from the inside to the outside. The convective heat transport is generally not even possible because you have closed cells, and even if you do, it's not going to be a large error. So the input energy measurement problem is, as far as I'm concerned, solved but not adequately documented. I'd like to have a paper on each one of these problems so that if it comes up, you can hit somebody on the head with it, refer them to it, and then they can be instructed by what's documented there. Now, one of these things that came up and was documented in a paper that we gave at the International Conference on Cold Fusion that Peter Hagelstein organized and chaired was addressed the question of whether or not defect energies, voids and dislocations and various things that are in the metal cathode could simply be released and account for excess heat. And I don't want to go into the details here. We looked at all of these, and the bottom line is that you cannot get the levels of excess energy that are reported, kilojoules and tens and hundreds even and thousands of kilojoules from the defect. So that one's done. Now, recently, I've been badgered by a colleague, Graham Hilbler at the Naval Research Lab, and he's basically saying, hey, there are a lot of water molecules in this experiment, many more than there are palladium atoms, and if there was some small, subtle change in the energy of the water molecules, water is a very complicated subject, could that energy manifest itself? Could it be released? So this is the beginning of a study that I hope to report at the conference in Rome in October. It's a plot that says this is the volume of the electrolyte, which turns into a number of water molecules, simply. And then on this axis, you have the energy that's released in the experiment, expressed as EV or joules. So you can say, oh, here's something over a kilojoule, and if you have that kind of a released energy and you think you can get a hundredth of an EV per molecule, that would require a volume of 100 cc's in the electrolyte. Now, you heard today talk about the megavolt energy releases, megajoule, I misspoke, energy releases from these cells. So you come across here and you say, well, it's not going to be an EV per molecule. That is, after all, a chemical energy. It's going to be something far less. So you wind up way down here. So you wind up at an electrolyte volume that just isn't possible. It wasn't in the experiment. So the only reason I don't say that this rules out the water as a source of energy, because there are some cases where it does fit the data, the amount of energy and the volume involved. But there are examples, like the one I just mentioned, where it doesn't. Okay, so I think that if this comes to the fruition that I expect, we'll be able to say that you can't have some small subtle effect in the rearrangements of the water molecules accounting for the excess heat. So to go on to the second part, the technical challenges are sweet enough, okay, but the programmatic challenges, the social challenges, the political challenges, all of these things make this a really, really interesting area to work in. I don't have to read mystery novels or do crossword puzzles or anything. This is fun enough. So I'll talk about the financial, IP, and communications aspects of this. So in a normal scientific field, government and investors provide funding to scientists and engineers who basically return technical information. And this cycle is dysfunctional on both sides. The money isn't there in general. There is or has been some DARPA money. There is some private money, some angels, a couple of billionaires are funding outfits. And there is some communications, the conferences and the websites and so forth. So it's not a blank set by any means, but it's far, far short of what it ought to be. Now, the situation we find ourselves in is that the really important people, the people listed in these boxes, are waiting for the scientific community to come to a judgment about whether or not this is a legitimate field of science. Okay, so we go to Congress, we go to the executive agencies, and what do they say? We're not scientists. We can't judge this. Only the scientific community has the wherewithal in order to be able to look at this and say whether or not it deserves funding. So they put questions down to the scientific community, and they are waiting for answers to come back. We go to the Patent and Trademark Office. Same song and dance. They're not scientists. They're waiting for the scientific community. Why do I list venture capitalists here rather than over here? They're not funding companies because the companies can't protect their IP in general. Okay? Then when you look at the journals, Science, Nature, the major magazines and the like, the editors say, we're not scientists. Same song and dance. Okay? So we're in a really, really strange situation where we need the American Physical Society, American Chemical Society, Nuclear Society, Material Research Society, and many others to look at this, as Rob did, okay, at the invitation of CBS, and make up their own mind. Now, I put the LENR community here with part of it sticking outside of the scientific community because we have some colleagues who are a few sigma outside the normal bandwidth, okay? We'll have a beer and talk about it. Now, this is not the exact words that Rob used on the CBS show, but this is the essence of it, to look at the data and do your own thinking. And, I have told people for years, I defy you to make these papers go away. They're done by credentialed people with adequate equipment and good controls, good calibrations. They stand up in front of the international community, present their papers, they respond to questions. Come on, you can't make it go away. Okay. Now, and the other thing to mention, these very vocal, very well-known scientists, in fact, I will say ex-scientists, okay, who are bad-mouthing this field, are in a really, really interesting position. Now the people involved were once ordinary scientists. They looked at the data and so forth, okay? But now I call them ex-scientists because they're no longer looking at the data, okay? But nevertheless, they have name recognition, and whether it's ego or money or whatever their motivations, they're simply not functioning as scientists anymore. Now, as the LENR community is set in the broader scientific community is set in the general community. So what's going on there? And this is a flawed but nevertheless interesting way of taking a look at that. These are the Wikipedia traffic statistics for the article Cold Fusion. So it's the hits on that article on Wikipedia for the month of March and April, rattling around 1,000 to 2,000 a day. Well, that's pretty interesting. That's 1/3 of a million people a year. Now, they may be useless students. I mean I'm a prof. I love them. Okay, but that adds up over the year. So this is the 23rd anniversary. There was the press conference that featured Frank Gordon, Pam Boss, Larry Forsley at the HCS meeting in Salt Lake City. Bumped up to, I think that's around 11,000 hits the few days after, decayed away, and then the CBS show, and it suddenly jumped up, and time constant is kind of interesting. So there is a broad interest there, but this isn't going to make the field into what it has to be. It's got to be that the key people, A, look at the data, B, make up their own mind, C, express what they have seen, and then we'll be where we ought to be. To finish up, as I say, I talk about energy in the U.S. in general, the current major and alternative sources, and then some possibilities for the future. This is a 200-year plot of energy in the United States, 1800, 1900, 2000. Wood came but never went, okay? Then coal became available, petroleum became available, natural gas became available. You see nuclear grew up here in the last half of the last century. So the situation that we now have is that the hydrocarbon fuels here and nuclear fission account for 92, I guess it is, % of the energy in the United States, and the alternative sources listed here are the rest. Now, I would like to pass a paper on, do a little test. How many of you would think that these alternative sources are going to grow to a point where they will significantly displace the things that are causing us trouble? Okay, I see some heads going like this. These, how many, you think they're going to grow to become major sources? They could, but the thing that concerns me is that they're tied to geography, hydroelectric, even the wind and the solar. They're out in parts of the country where the people don't live dominantly, okay? So the thing that I'm trying to sell right now is that some of the things that are not yet on the grid 1, 2, and others like Zero Point Energy may be as successful in displacing part of that as these hope to be. Okay, let's talk about hot fusion for a moment, okay? And again, out in TV land, there are probably some hot fusioneers, but I'll hear from them. This is the cartoon of triton, deuteron coming together in a fusion experiment. This is a plot of a half-century worth of funding of fusion by the Department of Energy. You see the time scale along here. There are two bars. The then-year dollars are the darker ones. The dollars scaled to the year 2000 are here. Became declassified, came along, had the OPEC oil crisis, and decayed down to, a crummy 250 or so million a year. Okay, that's where it stands now. The integral of this, somebody said earlier today, was 22 billion. Maybe that's worldwide, I'm not sure, but it's at the order of $20 billion that have been spent on hot fusion research. Well, here's the International Tokamak experimental reactor that's being built in the south of France. There's a human being to scale. This is the plasma volume. The last price I heard on that was $18 billion. Okay, so one experiment's going to cost about as much over the next decade or so as all of the hot fusion research up to this point. So, the WAG who said that hot fusion is the energy source of the future and will remain the same, may be proven wrong. Okay, but we'll see. So I'm trying to convince people that, in LENR we have a bulletproof database. It's real. It exists. We don't understand it and so forth. There are problems with it, but nevertheless, it deserves a sliver of the funding. So I wrote a short paper here arguing for the strategy for an LENR research program that has a base of instrumentation development, materials, and theory, has a core of experiments, repeating old experiments, doing new experiments, and then some engineering estimates on the top. If these sources develop, are they going to power your laptop? Are they going to power your house? Are they going to power a semi-trailer? Are they going to power a ship? There are many, many questions. So some of us feel that a 5-year program, it starts out like 20 million, ramps to 40 with an average of 30 million a year, which is to say something on the order of 10% of the investment in hot fusion in the U.S. alone, this would be a U.S. program, would be a reasonable thing to do at this time. It would allow us to support some of the people in the community and critically bring in people from outside the community, especially in the materials area. Very, very urgently needed. So we've made some real progress. When this started out, we didn't know whether this was incorrect, correct science, or a gray area in between. When some things come up, you don't know whether they're going to wind up being like N-rays or polywater things. They're going to be proven to be wrong, or whether they're going to be something that's correct, like string theory. Not technically correct, but correct as a legitimate area of scientific inquiry. Okay, so one of the things that has happened is that we've weeded this diagram. We're down to a point where at least we have science. In fact, if you look at the possible evolution from science to technology to engineering, it could hang up there. We could never get prototypes and products and profits at the business level or even higher level impacts. Okay, we just don't know where that's going. On one hand, on the other hand, some people, like a company in Chicago, they're trying to jump there. They hired a manufacturing guy recently. Okay, so thank you. I don't want to get hit with one of those cardboard things. Okay, so you can watch say a soccer game in 3 hours or so. You know the answer. Okay, this is going to take a long time to play out. And if you're among the younger people in the audience, just sit back. And even if you don't contribute, if you'll watch this space, this is going to be a really interesting thing to watch play out during your lifetime. Now, at my age, I'm hopeful that we'll get understanding before I run out of gas, okay? I don't think I'm going to be heating my home or driving anything powered by this yet, okay? Because that's going to take at least a decade and maybe 20 years. So the summary is that nuclear reactions are occurring in these experiments. I have people who ask me, what's the one statement? That's the essential thing. We're initiating them with chemical energies, okay? EVs to MEVs. Then somebody comes back and says, why isn't there an energy gain of 10 to the 6th? Well, it takes a lot of the EV things to get an MEV thing, and efficiency. I mean, it could be possible to generate nuclear reactions by chemical energies and have no hope of ever making a practical product out of it, because despite the 10 to the 6th gain in energy, you'd have so many fewer reactions that it would be useless. But this does have the promise of being something that's useful. So it may yield significant power it has yielded, significant power for noteworthy times, experiments that run for weeks, in some cases months. So there are major problems, reproducibility and controllability. You know, how would you like to have a car that turned itself on when it wanted, accelerated when it wanted, decelerated when it wanted, and stopped when it wanted? You know, too many of these experiments are like that. Okay, so we need controllability. We need quantitative understanding, overlaying theory and experiment. Exciting, in fact, historic possibilities of having distributed nuclear power sources with negligible prompt radiation and negligible radioactive waste. That's neat, okay? And that is very, very exciting. Potential applications, clean water. Frank Gordon mentioned desalination. Cleaning up the Ganges would be really nice, you know, among a few other things. In fact, the medical implications of having clean water, think about it, okay? If the U.S. could develop a nuclear industry based on these effects and export small nuclear heating units that would, of course, have to be reliable as well as safe and everything, I would not be surprised if it were more popular than Coca-Cola and blue jeans, okay, just to put it in scale. This is a big deal. Home heating, maybe electricity, portable power for electronics, and there's a long, long list of potential applications. So if you're in the field, you know the excitement. If you're looking at the field, you can enjoy what we're experiencing. If you are looking for a really good place to spend a career, I suggest that you take a look at this. So thank you for your attention. Thank you again.
Well, thanks for catching us up on schedule, too, and for a very interesting presentation. Here, what I'll do now is just shift off this, and our next presentation is from Peter Handel from the University of Missouri at St. Louis campus. And did you want to switch to your machine? We could switch.
Just plug in this one. I have did that.
Oh, okay, great. Sounds good.